this lecture we will see about placing rooks on an n cross n chessboard. Okay, so let us look at this problem more carefully, and this would use many of the techniques that we have learnt so far. We will use the principle of inclusion exclusion. We will also use the principle of the method of generating functions and so on. So let us start with an example. So this is a 3 into 5 chessboard. So place 3 rooks on a 3 into 5 chessboard. This is a problem that we will begin our discussion with. Okay. Rook is a piece in chess, and the property of that piece is if you place a rook in a particular position, every position in that row and that column is under attack by that rook. So, you cannot place any other pieces on along that row or column. Okay. Those will be positions which are attacked by this particular rook. Okay. So, we want to place rooks on the chessboard such that these 3 positions are non-attacking. Okay. So, one way of placing it would be in this particular manner. So, you can see that if you look at any of the rooks, they are not under attack from any other rook. So, what is this total number of ways of doing it? Okay. And note that we cannot place more than 3 rooks. The maximum number of rooks that we can place is going to be 3, because there are only 3 rows, and if we place more than 3 rooks, some row is going to contain more than 1 rook, and those are going to be attacking. Okay. So, our objective is to count the number of ways of placing non-attacking rooks on a board. Okay. Now, what is a board? The simplest board is an n cross m board, which is n rows and m columns, but the board could be much more complicated than that. For example, the red region that we are just marking out is also a board. Okay. Now, we could look at the problem of trying to place the rooks just in the positions indicated by that particular that particular board, which consists of the squares indicated. Now, how do we count this? We will learn 3 methods. One is based on, let us say, decompositions, and another is based on recursion, and the third method will be based on complementing. Okay. So, given a particular board, that is a subset of squares of an n cross m board, if we need to place non-attacking rooks, the number of ways of doing that, when we need to count that, we will use 3 generalized principles. One is the principle of decomposition, then another is a recursive way of counting, and the third would be to look at the complementary board. These 3 methods is what we will look at in this particular lecture. So, let us first look at the simplest case where the board is an n cross m board. Okay. So, if you have an n cross m board, we will assume that n is less than or equal to m, and we need to place some number of rooks, k rooks to be placed, and k is less than or equal to n. And the number of ways to do this is what we need to find. When it is a regular rectangular board with all positions being allowed positions, the first rook can be placed in the first row in m ways, and the second rook, so let us say you place it here. Any of the other rows, you can choose any column other than the one indicated by the first rook. So, the red squares are gone, the other columns you can use. So, the total number of ways of placing the second rook is m minus 1 and all the way up to m minus k plus 1, okay, if you had to place k rooks, and if k was n, this would have been the following factorial up to n. Okay. So, that is the number of ways of placing k rooks on a very regular rectangular board. Okay. We will introduce certain notations. So, small r k b. Okay. So, b is basically a board, okay, and a board, by a board what we mean is a set of allowed positions from an n cross n, n cross m chessboard. Okay. So, given a particular collection of allowed positions, the number of ways of placing k rooks on that board is denoted by Rk. So, this is defined as the number of ways of placing k non-attacking rooks. Okay. Whenever a rook is placed, you cannot place anything along the same column, you cannot place anything else along the same row as well. Okay. And if we look at this sequence R0b, R1b, R2b and so on, this gives the number of rooks, I mean the number of ways in which you can place k rooks in a board B. Okay. So, if we consider this sequence, this is going to be a finite sequence, because the number of allowed position is surely an upper bound on the length of this sequence. All the other terms after that basically becomes 0. Okay. And the generating function for R k b, k greater than or equal to 0, is called the Rook polynomial. Okay. So, look at the number of ways of placing k rooks on a board B. Okay. If you vary B, if you vary k, you will get a sequence, and the generating function of that sequence, namely R0b plus R1b times x plus R2b times x square and so on. Okay, Rn b times x raised to n. Okay. So, this sequence is called as the Rook polynomial. Okay. For example, let us do a couple of examples. If we look at this particular board, okay, there are 4 positions, and let us say all the positions are allowed positions. The Rook polynomial for that R0b is going to be 1, because there is only one way in which you do not place anything, and R1b, okay, this is going to be equal to 4. In fact, for any board R1b, the number of ways of placing one rook will be equal to the size of the board or the number of allowed positions, and R2b is going to be equal to, if you place a rook at the left side top corner, then the only place where you place a second rook is on the other diagonal. So, this is one way, and the other way of placing it is indicated by the red colored placements. So, there are only 2 ways of placing it, and therefore, we will get R2b will be equal to 2, and therefore, the Rook polynomial of this board, we call this board as B. The Rook polynomial we will denote by R, and the variable is x. So, Rxb will be equal to 1 plus 4x plus 2x square. If you take a slightly different board, okay, namely a board with 3 allowed positions. Now, R0, let us call this as B1, R0B1 is going to be equal to 1, and R1B1 is going to be 3, because there are 3 positions, you can keep a single rook in any of these positions, and R2B1, okay, the only way of placing 2 rooks is by placing it on the only available diagonal. There is only one way of doing it. So, Rxb1 is going to be equal to 1 plus 3x plus x square. The first thing that we will look at is how to compute the Rook polynomial. Okay. So, we could of course compute the values of RKB for all possible values of k, and from that compute the Rook polynomial. But the purpose of Rook polynomial is basically to do the reverse thing, that is, can it help us in figuring out the number of configurations possible, number of non-attacking Rook configurations possible. So, we will look at ways to generate the Rook polynomial, and once we have generated the Rook polynomial, we will use that to compute the coefficients. Okay. So, let us say we have a board. Okay. So, we will just think of this as an n cross m board in which certain positions are marked as not allowed. Okay. So, these are the non allowed positions, okay, and all the other positions are the allowed positions. Okay. And we need to compute R, if we call this board as B, we are interested in calculating RKB. In order to compute RKB, we will compute RXB, namely the Rook polynomial of this particular board, and once we have computed the Rook polynomial, from that we can derive RKB. Okay. The first thing that we will do is based on recursion. Okay. So, we will identify one particular position, let us say this is a position S in the board, okay, and all the placements of rooks on this table would involve either a rook on S or it will not have a rook. There are only two possibilities, there is a rook at position S or there is no rook. Okay. So, we will generate, so for each board, let us draw this board in red. So, given a board and given a position, so now we are interested in calculating the number of ways of placing k rooks on this particular board that is given. The red outline basically indicates the allowed position, the marked positions, the cross positions are the forbidden positions. Now, let us mark out one particular square, namely S, and look in terms of whether S is part of an arrangement, that is whether a rook is placed at S or not. Okay. So, if we look at all the placements, there are placements which involves a rook at position S and there are the others where there is no rook at S. Okay. So, we will construct two sub boards. One is the one where, I mean the first one we will consider is the board where we will ignore the position S. Okay. So, that we will call as the board B prime. Okay. So, B prime is the board without position S in it, okay, and that will have its own Rook polynomial. Okay. So, its Rook polynomial will be R x B prime. Also, we could have a rook at position 1, in which case, I mean suppose we place a rook at S, then what we will have is all these positions will now be gone. Let us draw it separately. So, if we do that, the remaining positions would be everything in the row and column would essentially be gone. So, this would be the remaining board. Okay, because these positions would be ruled out if we have a rook on S. Okay. So, that will be our board BS. So, BS is the board obtained by removing the column and row containing S, okay. And that will also have a Rook polynomial, let us call that as R x B S. Okay. Now, our objective was to compute R x B, okay. But let us just look at in terms of the number of ways of placing k rooks on this board B. Now, R k B is going to be R k B prime plus R k minus 1 B S. Okay, let us see why this recursive formula is true. The number of ways of placing k rooks on the board B is equal to the number of ways of placing k on B prime, that is after removing positions S, you do not put anything on position S and place k rooks on the remaining positions, or you put one rook on S position S and then put k minus 1 in the remaining board. So, k minus 1 in BS and 1 in S. Okay. So, this recursive formula we have justified why it is true. Now, from this recursive formula we can compute the Rook polynomial, we can give an expression for the Rook polynomial of B. Okay. So, what we know is R k B is equal to R k B prime plus R k minus 1 B S. Okay. We can multiply this expression by x raised to k, we will get R k B x raised to k is equal to R k B prime x raised to k plus R k minus 1 B S x raised to k. And now you can sum this up over all possible values of k going from let us say 1, because we do not want to take 0 because r minus 1 does not make sense. So, summation k equals 1 to infinity R k B x k is equal to R k B prime x k, again summed from k equals 1 to infinity plus summation k equals 1 to infinity R k minus 1 B S x raised to k, and this term is equal to summation j is equal to 0 to infinity R j B S x raised to j plus 1. Okay. And the left hand side term is almost the Rook polynomial of B, but just the first term is missing. So, we can write it as R x B minus R 0, R 0 is always 1, and the right hand side the first term is going to be the Rook polynomial of B bar or B prime. So, R x B prime minus 1 plus x times summation j equals 0 to infinity R j of B s into x raised to j, and this is the Rook polynomial of B s. So, this is equal to R x B prime. So, we can write this as R x B is equal to R x B prime, the minus 1 gets cancelled, plus x times R x B s. What we have managed is, in order to calculate the Rook polynomial of B, we can write it in terms of the Rook polynomial of a board with one less position and another one which has significant, which has one row and one column less. Okay. So, one position is less and here one row and column gone. Okay. So, we write the Rook polynomial of B in terms of its constituent terms, and we can do this recursively and compute the Rook polynomial of the entire board. Okay. But this could be very cumbersome if there are lot of positions. So, we will look at other methods. So, So, this can be useful for certain kind of boards. We will see other methods as well. Okay. The next method that we will see is called as decomposition. Okay. So, let us look at a special kind of board. So, let us say our board contained these positions. Okay. So, this is 6 positions. Okay. So, this is a board with 9 positions. Okay, let us call this as B, and we need to find out the number of ways of placing rooks on this board. We know that it is sufficient to find out the rook polynomial of this board. So, what is R x B? Now, note that this board is in some sense peculiar. It naturally breaks into 2 parts. Okay. So, what does it mean to break into 2 parts or decompose? Okay. So, the formal definition is, it means that the board can be split into 2 positions such that rooks in one position do not, in one board does not attack the rooks in the other board. For example, if I place a rook here, okay, and if I place a rook anywhere else in the other part, they can never be attacking. So, if you can break down the board into constituent parts such that any position in one of the part do not attack any other squares on the other part, then we call that as a decomposition. Why decomposition is helpful to us is because of the following fact: if the board decomposes into parts, the rook polynomial of the board is basically the product of the generating function, or is the product of the rook polynomials of the constituents. Okay. So, let us call this board as B1 and this is B2. We will see that Rxb is going to be equal to Rxb1 into Rxb2. The proof is simple. If we look at the definition of rook polynomial, Rxb is equal to R0 plus R1b times x plus R2b times x square and so on. Okay. And here the number of ways of placing a rook in B1, k rooks in B1, that is given by the rook polynomial. So, that is going to be, let us say, I will write it as R1 to indicate that we are looking at board 1. So, R0 plus R1 1. So, we ask ourselves this question: how do we place k rooks in B? Okay. So, we could think of it as 0 rooks in B1 and k in B2, or 1 in B1 and k minus 1 in B2, 2 in B1 and k minus 2 in B2, all the way up to k in B1 and 0 in B2. Okay. And all of these arrangements are going to be different arrangements because they have different number of rooks in B1 and B2. And notice that we could do these part and these part independently, because any placement of rooks in B1 is not going to attack any positions in B2, and this is exhaustive because if you have to place rooks in B, there has to be some number of rooks in B1 and some number of rooks in B2, and their sum should be k. And so, therefore, the total number of ways is going to be equal to R0 B1 into Rk B2 plus R1 B1 into Rk minus 1 B2 all the way up to Rk B1 into R0 B2. And this basically is just the convolution of the 2 sequences. If you look at the sequence corresponding to B1, so R0 R1 up to Rk, and the sequence corresponding to B2, and if you convolve them, if you take the convolution of the 2, you will get the kth term of B. Okay. So, this is summation I going from 0 to k r I b 1 times r k minus I b 2, okay. And therefore, I mean if the terms have this particular property, then we know that it is just the product of the, I mean if we look at the Rook polynomial or the generating function, that is just going to be the product of the constituent generating functions, okay. So, this is a very useful thing if the boards can be naturally decomposed into parts, and it applies even if you have, let us say, more part. If you had a board where there were elements, the three elements here, again if this is B3, the Rook polynomial will be just the product of the Rook polynomial of the constituents, okay. The third technique that we would see is something called as taking the complementary board. So, here we will use the principle of inclusion exclusion. So, in general, the number of allowed positions, if they become too large, then the decompositions are also going to be difficult, and the recursive formulation is also going to be difficult, because there are too many positions to handle. But if the board is having a lot of allowable positions, and if the complement has, let us say, significantly less, then we can use the complementary board technique. And for example, if you had a board with all these positions, but very few missing positions, okay, if you have a board of this format, you can see that the complementary board is a very small one, it has just 3 allowed positions. So, we will denote a board by B, and for this discussion B prime denotes the complementary board. The complementary board basically contains all the positions which are absent in the current board, okay. We can look at Rook placements on the complementary board as well, it is just another board, okay. Let us look at how this technique is used. So, we will introduce some notations. So, let AI, so let A be the set of in all Rook placements, okay. So, A is the collection of all Rook placements. For example, if this was an n cross m board, okay, we do not look at the forbidden positions, I mean we will allow rooks in all positions, the only requirement is they should be at non-attacking. So, A is what we denote that set by, the set of all possible Rook placements without considering what is allowed and what is not allowed, okay. So, we need to think of a bounding box for the board, a rectangular bounding box, and in that the set of all possible placements is what we will call as A, okay. And AI will denote the placements which contains a forbidden square in the ith column, okay. So, look at any particular placement, suppose we had placed rooks in the following manner, one here and one here, okay. This will be a Rook placement, but it is not an allowed, I mean it is not a placement which we want to include in our counting, because there are 2 rooks in forbidden position. Of course, this is not even a, sorry, this is not even a valid placement. Okay. So, consider the orange positions, that is a placement of rooks, and this is not to be included in our count because there are 2 rooks at forbidden positions, okay. So, if we consider A4 and A7, okay. So, this would be a placement which will belong to the set A4 and the set A7, okay. Because in the fourth column there is a forbidden square on which there is a rook, and in the seventh column also there is a forbidden square on which there is a rook. The total number of rook placements was easy to count. We can denote that by P M n, okay. So, this is the number of ways of placing n rooks on m columns, or placing n rooks on an n cross m board. Okay, we can assume that m is going to be larger than n. If m is less, then we cannot really place n rook, the count will automatically be 0. Okay. So, A is just going to be P m n. Now, we need to basically find the number of rook placements on B, and that is basically the same as find the number of, find the size of A1 union A2 union AN, sorry, AM, the whole complement. Okay. So, A1 union AM, if you take this set, the union of that basically consists of all placements in which a forbidden square is used. If you take the complement of that, none of the rooks will be on a forbidden square, and this set size is what we need to consider, and that is where we will use inclusion exclusion principle. So, we know the set of the size of A. So, A minus A1 union AM, if you compute the size of A1 union AM and subtract it from the size of A, you will get the number of ways of placing rooks on the board B. Okay. So, how do we compute these things? Okay. So, we will basically be using the inclusion exclusion principle. So, while we are using the inclusion exclusion principle, the terms that we need to estimate are, so let us say A1 or let us say AI1 intersection AI2 intersection AIK. Okay. The size of this set is what we need to estimate, and this summed up over all subsets, summed up over all I1 IK. Okay. Let us denote this by NK. Okay. NK is what we need to find out. Okay. So, if we can find out the value of NK, then the count that we want is just size of A minus these, plus or minus these NKs, okay, by means of inclusion exclusion. So, NK denotes the number of ways of placing rooks, okay, sorry this. So, look at the inner term AI1 intersection AI2 intersection AIK. Okay. So, this is a set of rook placements such that there is a forbidden square in I1 and I2 and IK. So, if we look at the complementary board, these positions are valid positions for those are positions, those are allowed positions. Okay. So, we are placing K rooks on I1 to Ik, okay, and the remaining n minus k rooks can be placed in n minus k p n minus k times, okay. So, A1 intersection AK basically denotes the set of rook placements such that the forbidden squares in I1, I2, Ik etc. are being used, okay. Now, if you consider the complementary board, these positions are valid positions or allowed positions in the complementary board. For this particular choice I1, I2, Ik, there were, let us say, there were t ways of doing that, okay. The total number of ways of placing rooks would be, placing n rooks would be t times p m minus k times n minus k, because if k rooks have already been placed, we have taken away k rows and k columns. The remaining m minus k columns and n minus k rows can be used. So, t into p m minus k n minus k ways are there to place rooks, okay, and where this t is just the number of ways of placing rooks on the complementary board, okay. This is for one particular I1, I2, Ik. If you sum it up over all possible I1, I2, Ik, that is going to give you the total number of ways of placing placing k rooks on a on the complementary board. So, we can write Nk as equal to p m minus k n minus k, this is going to be the common factor multiplied by the total number of ways of placing k rooks in B prime, okay. So, this is going to be equal to p m minus k n minus k times r k B prime, okay, and therefore, R n B we can just write it as p m n, this is the total number of ways. Now, we can apply inclusion exclusion minus n 1 plus n 2 and so on, and n 1 and n 2 we already know, this is going to be p m n minus p m minus 1 n minus 1 into r k B prime plus p m minus 2 n minus 2 times r k, sorry, instead of r k this will be r 1 and r 2 B prime plus and so on, okay. So, if we can compute the Rook polynomial of the complementary board or the number of ways of placing rooks on the complementary board, from that count we can compute R and B by using the principle of exclusion. Okay, we will stop here.